as the other days, I built a notebook in a way that if I'm talking and you prefer reading, all the information that I'm saying is in the document. I'm not saying anything new. Probably the document is better expressed because I did it when I was awake, and now I'm feeling a bit jet lagged. So I have the feeling that I'm going to make more mistakes talking than actually if you read these things. But another important thing is, as I said, bioconductor, every package in bioconductor, let's say, needs to follow some rules about documentation. Documentation is great. And they have one thing that I call vignettes, which pretty much tells you how to go step by step through the process of doing analysis. DSIC2 is not different. There's still things that are not always on the documentation, because it's something that you learn by practicing, right? But the documentation definitely should allow you to go through every basic step. And DSIC2 gives you a lot of recommendations. They have an FAQ with questions that I guess that they received through the years, and they give you examples of how to troubleshoot whatever situation you are in. So there's a link to the vignette of DSIC2 that is very well documented. So you know, guys, what we're doing here with this library function, what we do? Yeah, we call the libraries, we call tools that we may need, right? If we do the basic analysis in R, we are not going to have DSIC2 available. So basically, we're telling, OK, we need DSIC2 for our analysis. Tidyverse, we use it the first day, is the one that allows us to use that percentage bigger than percentage to do pipes, right? That's the tidyverse way to doing pipes. And it gives us also GG2 plots, where you can make cool plots. We're going to use what we call pretty heat maps, beautiful heat maps. This is just some colors, nothing important. This is a library used by DSIC2. I'll go into details later. This is an open source way to create Excel files. So what I like to do with when we do analysis in DSIC2, instead of exporting tabulated tables, I prefer to create an Excel, so you can open in your computer an Excel file. This is a minor use. You don't have to use it. It's to create. I use it to create interactive 3D plots. And because I don't like Bonnie's way to plot volcano plots, I use what we call enhanced volcanoes. Do you have, by the way, any library that I'm using here, like pretty heat maps, you have other libraries that do the same job. I just pick one that I like, right? But there's a lot of alternatives to everything I'm saying here. This one here is just these options are used to create the window where we plot in Jupyter notebooks. I'm choosing the size, right? Because sometimes the default ones create tiny plots. I want to see the display a little bit bigger. So this is how I say to create a wider or taller display size. Probably I'm going to use this call later on in some spaces because I prefer wider or narrow plots. So just to let you know that that's what it is. Well, I'm telling you what this line does, and that's the only thing this thing does is telling me the time of the day. That's it. So, like the other day or the other days, the only thing we need to do is just execute it. So you can do it. Don't wait for me. You're going to get a bunch of warnings. That's normal. Oh, one thing that you should know about R. Let's see if I found an example here. Yes. Yep. You see this section of conflicts? Basically, it's telling you that there are packages, or when you load a lot of packages, right? So they come with functions, like, I don't know what function we used, like plot function, right? Yep, that they may have the same name in two different packages. So that's what the conflict is, when you have two functions with the same name in two different packages. Yep. So it's telling you there's going to be some conflicts. It's not going to affect what we do, but you should be aware of this issue in R, right? When you load a lot of packages, some functions may have the same name. So Actually, the best practice you could do is when you want to call something and you know the package that it comes from, when you call that function, call it with the full name. So the full name would be the name of the package, so Dplyr, collapse. So if I want to use collapse from Dplyr, call it with the full name instead of calling collapse. Because if you call collapse, you may call it from Dplyr or from iRanges, right? And may depend on how the order of things they call your libraries, right? So this is what it's telling you, that Dplyr, if you call collapse, you're going to use collapse from Dplyr, not from iRanges. That's what this thing is telling you. If you want to use the iRanges one, you're going to have to call it as iRanges, collapse. Because if not, it doesn't know which one to use. So a good practice could be to call your functions with a full name. We don't do it here, but it could be a good practice to do. Let's talk a little bit about the data we're using. The data comes from this paper, and I hope I remember the details. So what they did, they created a knockout, right? The Shank3 knockout, Bonnie, I think that's what they did. And then they put the animals to some sleep deprivation. And they did the comparison, and they come out with some conclusion, right? Related to circadian rhythms, I guess. We don't care much about the goal, so we're going to create our own goals in this analysis. But just to let you know, if you want to know details, the data comes from this paper. So it's the original data they use in this paper. And you're going to notice we're going to come out with a different conclusion. Not the one in the paper. I never went through the paper to know exactly how they did the analysis. I don't remember the details. But it's not the same results we're going to get. So I guess that happens in science. We are not following the same analysis steps they did, but I'm wondering what they did. I don't know. One day I need to redo the analysis in the way they did it. I never done it. We never have the time, right? But I don't think they use DSeq2. But if you have time, if you click here, it's gonna you're gonna go to the paper, so we can check exactly how they did it. So another thing I did, so I created the row counts myself. So these are analyzed pretty much in the same way you did yesterday, which it doesn't mean is the way they did it. So this is how we're going to be reading our count metrics. So you use already this, right? Read CSV. And we're telling that they use the first column for row names. So these are our genes. And everything else is going to be transformed to a matrix. That's not important in this case, because DSeq2 also would do the transformation for you. But instead of having a data frame, we have a different structure, which is a data matrix. Oh, and why we do this? Right? Why we're doing this? We're getting the first rows. By why we do it? We want to be sure we are loading the correct data, right? Always visualize what you do is always good. Be sure that you created the right object. I guess it goes to sleep. So if I want to, oh, by the way, it's too small or not in the back? Should I increase this? Okay. What about now? More, less? More? Okay. Is this the same? Whatever it was here before is the same as this or not? Yes. I'm just printing the count data and had only taken the first two. This is a pipe, right? Where we said, actually I should do these all the time, but I keep forgetting. So in that way we get used to this concept of Dplyr. I recommend it. It's a really cool tool, and it makes reading what you're doing, I think it makes reading your code easier, right? So I get in the table, give it to head to just print the first 6 lines.
What other, like when you're drawing the head, you can also run like head, parenthesis, and count data same day, and then like what you guys did yesterday. So both is actually same. Can you please expand it more?
More zoom. I'm going to run out of screen space. Can I?
Maybe one more.
Yep. So we got the table. So the first issue is that, right, we have a really weird names for samples that doesn't tell us much. So we're going to have to deal with that later. But yeah, it looks like we uploaded the table. Another thing we mentioned yesterday, the gene names, right? They have double annotation here. So we have the ensemble ID for the gene and the official gene symbol. It's mouse. Yeah, yeah. Sorry, I should have told you this. We didn't sleep-deprived humans in this paper. We sleep-deprived mice. I'm sleep-deprived, but the mice also were sleep-deprived. You keep going. I'm not going to read this. So I think for you guys, the best thing you can do, it's easier for you probably, is if you create your metadata in Excel and read the file, probably, or a tabulated table. Generally, it's better if you create, don't save it as an Excel file, save it as a tabulated table. It's easy to read. That's probably my recommendation. And you create your metadata. If you need to create your metadata, right, you create that table on Excel, for example, and then you import it to R. But if you want, in R, you can create data frames, right? We've seen this before, I think probably the first day. This is a vector where I'm giving the sample names. I'm creating another column telling it if it's what type of the donor of that sample. I'm creating also the treatment, if it's been treated or not. I'm assuming it's what I did here. And then I'm creating a data frame with these two columns and adding the sample names as the row names for that metadata. If you run this is a way to create a table in Excel, right? In Excel, in R. Right, so all that code creates this table. I have the feeling for you guys, if you don't want to deal with coding, you can just create a table in Excel and then import it to R. Oh, did we import the metadata at some point? Oh yeah, what I was trying to say earlier, right? So these sample names doesn't give much information about what they are because they were downloaded from GEO. These are the sample IDs. This is the metadata, the file. Any questions? I'm going too fast or not? Sorry, I probably should stop in every step and explain what we do. You know that read CSV, right? I'm just reading the table. Oh, yeah, yeah. So the objects that I'm creating, you can name them as you wish, right? I'm just giving names of the terminology because I think it's easier if we talk about metadata, call it metadata. But actually, DSIG2 call it call data, column data. They call it call data. But I think metadata, for me, I understand it better, so I call it metadata. But you can call it whatever you want. And the only thing we're doing here is just reading this is the metadata, the file we saw earlier. Again, the same thing. The row names are the first column. And every string here is treated as a factor. So it is not treated as just text. It indicates something. It's a factor of your discrete variable, right? it's a knockout of the gene JANK3. Yeah, so SHANK3, I don't know what SHANK3 is required. I'm not sure. Oh, okay. Oh, okay. So SHANK3 is the name of the gene that was knocked out. Sorry if I haven't been explicit about it. So the metadata. We'll talk about it. Just execute it. Don't worry about it. Google it. Or if you don't want for me to explain it, you can Google it. But don't worry about it. It's not important now. This is the metadata. So we have the genotype. We have the condition, being sleep deprived or not. For the purpose today, or the first part today, we are not going to care about the genotype for now. To make our analysis simpler, we're going to care about if it's being sleep deprived or not. So we're going to focus our formula, right, is going to be that we're going to assume that differentials, the gene differential or the differential expression we observe in our data is going to be caused by the condition, being sleep deprived or not. That's going to be the assumption today, or for the first part. You have the explanation next. Another important thing that it's a good practice, again, you don't have to, but I think if not, you may encounter problems later, is to level or relevel your factors. So our factors are really simple. We have only been, so remember we said the condition are considered factors. Our factor is being normal, normal or sleep deprived, right? So whatever we use as a base, right? So I think DC2 takes it as alphabetical order. So I don't know how we call it, normal and sleep deprived, I think are the two conditions. So normal is going to be considered our baseline. But let's assume you have a lot of treatment 1, 2, 3, 4 to 5 or different names. So you can be really explicit about what is the first level in our factor. So let's be explicit just in case, and we can practice it. So you remember what this means? So metadata is our data frame, and we are calling the column genotype, right? And we are releveling the genotype column, indicating that wild type is going to be our base level. Now, you're going to have to relevel the other two. What is going to be our base level? Well, yeah, yeah. So double check whatever the metadata says, right? So if you type normal with uppercase, it's not going to know what you're talking about, right? It needs to match whatever is in your metadata, which I don't even know if I type it correctly. Again, everything I'm explaining is explained before or after the code, right? I mean, you can even have the levels in a specific order, like low, medium, high if you want to, and so on. So let's do one thing before this happens again. Try to relevel, and I'm going to plug in the computer so it doesn't go to sleep. Thank you. Condition is normal. As a reminder, remember the trick using autocomplete and tab. So if I start typing metadata and I press tab, it should give me all the options for keywords that start with meta, for example, metadata. So you don't have to type every time the whole thing. It's normal. Are you copying me? Don't copy me. I may do something wrong. This condition is normal, yes. And wall type is the other one, yep. Is wild type? No. Is wall type normal, underscore normal. Any issues relabeling? You're not going to get any information if what you did is correct or not. So again, if you are new to coding in R, it's always good to check what you're doing. So you could, I think if you call level or levels in plural, I would. Oh, no, it's levels. If you want, you can check the levels in your columns by just typing levels and the column that you want to check, and it should give you whatever you decided was the first level, right? So this is a situation where maybe, right, the column genocondition, which is the combination of the condition and the genotype, where you have multiple levels. This is an example where you may want to resort them in a specific way for whatever reason. You could, right, because you have multiple ones. But in the case of the genotype, you only have wild type and another one. So if you know that DSIG2 takes them alphabetically, you may skip this. I still think it's a good practice to stop and think, what is the baseline? What is your baseline? What is your reference, right? So it's not bad to use explicitly and tell what you're doing.
Commands at the same time. The animal used will be right type and the condition used will be normal. That is my reference base level.
So sorry, start again. I'm slow today.
No, I'm taking the two parameters at the same time in account by giving this command.
Which command? The level one?
Genotype as well as the condition.
Oh, you mean the third column. The third column, yeah, it should have explained better. Yeah, the third column in the metadata. Yeah, I should have explained better. Sorry, yeah, I should have stopped and explained this. My bad. So first column is clear, genotype. Second is condition. What I did here is to combine these two in a single factor. That could be another way you could do an analysis, right? We can do the analysis considering genotype alone, condition alone, combine them in a way that we have 4 different states and mix them in one. That could be a way to do the analysis. Or we can use complex formulas and use the genotype and condition in our model separately but in the same analysis. So I guess my recommendation is don't do that initially, but there are ways, I mean, you could do it. And actually it works well too, right? What I tend to do is keeping everything separated and do an analysis like that. But again, this is normal, it's fine. I mean, you're not going to get wrong doing the analysis.
Expand your table, making multiple columns and then pick.
Well, you don't have it. Yes, you don't have to do these for every analysis, right? But I'm saying, let's imagine you want to do pairwise comparisons. That's what you're going to do, right? And you want to compare, for whatever reason, wild type normal versus versus the knockout normal 2. Then it's easier to create a column with those data and then compare them pairwise. But if you want to know, let's phrase it differently. If you want to know the coefficient factors of every variable in your metadata, you need to have them separately, right? If not, you're just mixing everything here.
But the genes, what we are referring, what we are finally analyzing, that will be according to this one condition, right? This is just to name the our group.
Yeah, so here you're creating the grouping that you want to analyze with this table.
Yes, and the genes are per group. Whatever genes we are analyzing.
You're creating the groups here.
Yes.
This is the definition of the groups.
Yes.
Yeah.
So
So
every comparison in our data set or in this data set, it's between the groups.
yes,
And the genes vary between the groups.
yes. However you define the groups, which it could be just taking one column into account, another one, combine them both together. But the main issue of combination is that you're not going to know the exact effect of wild type and normal separate. You're just mixing. Then you need to make the internal effort to interpret that data of what it means when you do the pairwise comparison. But DSEQ2 have the power of telling, if you give me these factors separately, I can estimate the coefficient for genotype and the coefficient for condition separately. So that's why I guess my general recommendation, if you have this type of situations, first try to do separately, and then if you think that it's better to combine for whatever reason, and there's reasons for that, you could do it. So no problems, relabeling, everything is good. So next part, we haven't touched DSEQ yet. So we're just doing checks that everything looks good, our metadata looks good. So another step is to see that metadata and count data are compatible, right? So any thoughts about what is happening here, the first line? All is going to just return true or false.
So rows have data, the columns, we are defining our columns and our rows.
We are not defining them. So this is going to return the row names of metadata. This is going to return the column names in our call data, right? The row names in the metadata, what they are? No, metadata, the samples. Yep. They are the samples. The call names in our count data, what they are? No, the samples, true, they are the samples.
Sample 1, sample 2, sample 3.
Yeah, so these are samples, these are samples. So basically we're saying that the metadata table that we have, the row names or the samples names, are present in our count data. So we are checking there are not misspellings, nothing weird. So basically, if all of them are present, all returns true. That's what we're doing here. Okay, next one. Well, I'm already saying what it's doing here a little bit. We've seen this before, I think, at some point. So this is our count data. The way to access the count data is by row or column, right? So we are giving our samples to the count data, saying we are subsetting our count data to only use whatever is in the metadata. That's what we're doing, and store it then in our count data. So if our row counts have more samples than we have information for, basically we're excluding them. So we want that all samples in the metadata are represented in the count data and the other way around. We don't want extra information because DSEQ is going to tell you, oh, you're giving me extra samples, what I do with them. So we are subsetting our count data by the column names that are present in our metadata. That's what it's doing, right? And storing that in count data. In our case, it's not important because everything matches. So there's nothing happening here. But it could be a case that you have a count data that has a lot of samples and you only care about a fraction, or that's the one that you have information in your metadata, so you're subsetting. So the square brackets, what they're doing is the first value in before the comma is saying, take all the rows, because I'm not subsetting. The second is take the columns that are in the metadata. That's basically pretty much what we're doing. What about this one? So it's similar to the one on the top, but it has the identical. Any thoughts? I mean, there's no wrong answer. We haven't seen these before, so they need to be in the same order. So if you read the text, I mentioned that they need to be in the same order. So this is checking that it's in the same order. This line is useless for one reason. Because when you subset, actually uses the order you give it. So it's taking the order that is in the metadata and sorted the count data based on that order. So this is just going to return true no matter what because we run the second line. So if you run, it tells you, yep, so it's true, everything is present, we're good. It's true, everything is in the same order. Just a sanity check. And if again, everything I'm saying, and now I'm realizing everything is here, so I'm not, if you notice that I'm explaining something right, give it a look at the text because it's explained. I'm probably better job that I'm doing. Not much. A few seconds. Less than a minute, I'm assuming. We talk about these, right? So I said we're going to take the simple example that our expression data is based only in condition, beta has been sleep deprived or not. That's our expectation. So these are going to be our formula. I always like to put examples of how you phrase your experiment. I think that helps when we deal with investigators, right? I'm giving, let's say, different levels of expression. So with that formula up there, right, what we're saying is that DC2, the gene expression levels depends on the experimental condition, being sleep deprived or not. If you want to do statistical phrasing, the models assume that the variation in expressions can be explained by the condition variable. That would be, and if you go the equation style, right, that would be how internally R read it, right? It says the expression of each gene is its model and as a function of the experimental condition. I don't know. I have the feeling that sometimes expressing what the model means helps a lot. And we're going to do an exercise later about it, especially if we take into account more complex models. So I always try to, when we collaborate, try to make the investigator to express what's the goal, right? Our goal is we are assuming that our condition changes the expression levels. I know it's really simple, it doesn't make much sense now, but if you have a complex metadata table with a lot of factors, it helps to phrase it a little bit, or make the exercise to phrase what is your goal so you would understand how to build the model. Okay, what we finally expected to run, right? So you don't see it here, but you can see the let's do the proper. In R, for example, you can break lines. If you break them in functions after a comma, and not going to be a problem reading it. We don't need that / like we use in Bash. So it's clear what we are providing, right? We don't need to go through this. So the first thing is just telling, read the data matrix we created object DDS, and now this function here does everything I mentioned, normalizing and doing the statistical analysis. It does everything. So and I hope it doesn't crash. AWS is giving me trouble today starting it. I hope we don't have any issues. Did any one of you finish the whole thing? And it's okay. So some people already finished. Don't worry about the warnings. If you type DDS, which is the object that we created, you're going to get some information like this. So it's not going to print the whole object out, but you could access all the information inside. And we're going to see how we're going to access that information. But in here, you have everything, like the normalized counts, analysis, et cetera, et cetera. So we already talked about the size factors. That's the size factors, that complex steps that we took on the presentation that is used for normalization. You could check them, right? So every sample is going to have a size factor. So the way to access, the way to access is with this called size factors, DDS, and it will print out the size factor for every sample. The as data frame is just to make it nicer to look at it. That's it. There's nothing special about it. And again, I probably could do this to make it, to be consistent in the way we should do it, right? So it's going to be hard to show on the projector the values. I think I'm asking a question, right, up here. Can you guess which one is the one that has been most sequenced or has higher depth of sequence, and which one is the lowest sequenced? I don't see the whole table. You're going to look at your own table because I don't even know. Remember, the size factor is what DSeq2 is dividing your counts with. Any takes on what sample? You don't have to give me the name of the sample. You can use the size factor to figure out which one it is. Which one is the most sequenced? We are dividing our row counts with the size factors. Which one do you think is the one most sequenced? Remember, normalization takes into account two things, which is the sequencing depth and the composition, based on the steps that I mentioned in the slides. The one with the highest is going to be with a higher number, right? That's, you already can tell which one is the one that has the highest depth. I'm assuming it's this one. All the numbers look like. Yep. And this is the one with the lowest value, right? Probably. Yep. So that is the other way around. This is the one with the lowest sequencing.
So pretty much the size factor basically tries to make the amount of rows we have uniform, right?
Yep.
Like it's kind of basically
To be able to compare them, right?
Yeah, it's accounting for like that some samples have more rows because we got more data.
They have more counts, no more. All of them should have the same rows in theory in our table. So the ones that have more counts, yes, that's what I'm trying to do. In addition to the problem of the composition that I mentioned, right? Ideally, right, if you do a good experiment, you want everything around 1, because then you don't have to force the normalization process to change your numbers, right? That would be the ideal. So can you make decisions based on the size factors? Normally we don't. You could, in the sense that you could keep track of saying, oh, maybe this one has a very low number. It could be an outlier. It could be that we didn't sequence enough, right? And when you do PCA, if you see that sample, in one of the extremes of your PCA, you say, oh, maybe that sample needed more sequencing. The size factor are pushing too much the data, and it's creating artificial signal, right? Normally, you don't have to make those decisions, but you could check them, right? So what we're doing here, I mean, R can be easy to read sometimes, and I think this is the case.
So it is based on the count data.
We're taking the count data, yes. We are not taking the DDS object here. Yep. It's just called sums, right? The sum of the column and reporting. So if you want to double check what we said, this is the sequence. This is the more or less the sequencing depth. This is the counts that we got, right? So you can check if we were right or not. I think this was the sample with the highest depth, which is 7 million on counts, and around here, yeah. That must be no. One of these is the lowest, I'm assuming, around here. Yep.
So these are the count of genes.
Those are the counts of the genes, the sum of every column. That's what it does. It doesn't do anything. Again, if you don't work for me, you can keep reading. Everything I'm saying is on the Jupyter notebook.
Count of genes. Sum of count of genes. Right.
Call sums just returns the sum of every column. It gives you value for every column. Every column in your count matrix is a sample. Again, I'm insisting on the formula, but we already been through this. This is another way to represent it, right? I like a lot the way to use the arrow system to have it in mind, meaning, so this is our formula internally how R uses the linear models, which is calculating the intercept. If we do linear regression, you can call it intercept of the baseline. So it's estimating what is the value of this. So from 0 to my average for that condition, and then estimating from the baseline to the average of my treatment. And these are what we call the coefficients, right? Or in our case, this is going to be our fold change. What is the fold change between the baseline, control, and treatment? But I like to use the arrows because, again, if you, even in a simple example like this, which you don't need to do this because you already have the mental image of I'm comparing two things and I want to know the fold changes, having even a simple example, what happens internally is going to help you to understand more complex examples. Or not because you don't care, because you always deal with simple examples, you don't need to do these things. Okay, so how we access we could, again, everything that DSIG2 needs to do is already been done. The only thing we are doing is exploring the object. We could access the coefficients, which coefficients in this case are the fold changes. So if you do this, you're already accessing the coefficients we are calculating in our formula. This is the baseline. What is the baseline? The average expression in our normal. So this is our baseline. And this is our fold change. And yeah, in the way that it's built, yeah. So it's readable because we're giving it readable columns. If we give him something weird in our metadata, it's going to be harder to read. But basically, DC2 creates this. So I'm taking condition, the column condition, and I'm comparing this versus this because this is our baseline, and this is our fold change. You probably are not going to do all the steps we're taking. You're probably not.
Why is it showing only for the 6?
Oh, because I'm using head. So head. So again, let me do it. Let's be consistent. I don't know why I wasn't consistent this day when I type all this, but I want people to get used to this. So if I only give it the first part, coefficients DDS, would print everything. But I'm giving everything to head, and head only prints 6 lines.
So here we are getting the average of baseline. The value is 10, suppose.
Yeah, so
And the fold change between two conditions. But we are not getting value of the condition. Like it's 10 for the baseline.
so
Value.
sorry, what do you mean? I'm not following the question.
So here, this 10, what does it represent? It's
So for you, so the simplest explanation of what is 10 is the average of your baseline, normal. That's the average expression of normal. That would be the phrasing
Yes,
for,
but
for us, for normal people.
what about the average of the conditions?
You can calculate it later, but this is not what it's doing. This is giving you the coefficients of your formula. Your formula is baseline plus condition. So baseline plus your coefficient. So this is the beta. Did it die? No.
For one gene, it was showing NA. Why was that?
You probably don't have data. So there's no counts for normal, there's 0, or there's another reason. It could be, it's, so every step we're taking, you don't have to do it in your analysis. We're just exploring the data. You're barely ever going to run coefficients. You don't care, right? Generally, we're going now through all these steps is just to explore and understand what is happening a little bit in the background. But using the coefficients part of it, you barely ever, I don't do it. The coefficients are on your final table, are your 4 changes anyway, right? You want to know the p-values, the 4 changes, you don't have to do all this. It died for everybody, but it's me. Okay.
So we can add p values to it along with the code.
Okay, so again. Oh, it's the network, it's not AWS, it's not dying? Okay, woo. Okay, good. So again, we are not accessing the results yet. The only thing we access with coefficients are the coefficients of our formula. That's it. Yeah, we can, well, yeah, let's take the break now. It sounds good. I'm happy to stay and answer questions. I understand this is complex or different, so I'm happy to stay and answer questions. So the question here is we can access the p-values and all that. We'll access that later. So what we're doing here is exploring our data. And with that function, the only thing we ask dseek2 is give me the coefficients. And the coefficients are what the formula is, which is the baseline and our 4 chains. That's it. But again, if you have a complex model, right, this table is going to be much bigger. You can ask if an example we had yesterday, right? It was genotype, sex, and condition. This table will be much bigger. You generally wouldn't do anything. Oh, it's going back.